Good evening, everyone. In the last lecture, we had left with the mutual inductance, right? We had discussed the concept of the self-inductance, right? So, in case of self-inductance, we discussed that whenever a flux changes inside a coil because of its own change in the current, the magnetic field inside a coil changes. Then, because of that change in magnetic field in its own coil, the EMF or the current gets induced inside a coil, right? EMF or current gets induced in a coil. So this is what we discussed in the last lecture. That let's suppose this is the coil. In this coil, if we change the current, then because of that change in current, the magnetic field inside the coil changes, and because of that change in the magnetic field, the magnetic flux changes inside the coil, and due to that, the EMF gets induced. And then we define the coefficient of self-inductance as well, right? In the same way, let's suppose that if we have two coils here, one we call as primary coil or the primary circuit, another we call as secondary coil or the secondary circuit, right? So we have two coils here. One is the primary coil, another is the secondary coil. So here in the first primary circuit or this primary coil, we have N1 number of turns in the coil, and V1 is the magnetic field because of its own current, and L1 is the coefficient of the what we call as self-inductance, right? And similarly, N2, Phi2, B2, L2 are the flux linked with the secondary coil, and N2 are the number of turns in the secondary coil, and Phi2 is the flux through the secondary coil because of the magnetic field of coil 1, right? So, so this is how we actually understand by the mutual inductance. It means that if the magnetic, if the flux because of the secondary loop gets changed in this primary loop, then in the primary loop, because of the change in magnetic flux, the EMF gets induced, right? EMF gets induced. And in the same way, if we change the current in the primary circuit, then the magnetic field in the primary circuit gets changed, and because of that, the flux in the secondary circuit also changes, and due to that, the EMF gets induced. So this is a mutual inductance, right? This is a mutual inductance. So if there is no change in the current, then the magnetic field will not change, and there will be no concept of the mutual inductance, right? Or no concept of the induced EMF, right? Because when the current does not change, the magnetic field will not change. If the magnetic field will not change, the flux will not change. So induced EMF will be equal to zero, or we can say in this case here, induced EMF will be equal to zero, right? Induced EMF will be equal to zero, is zero. Now the question is that what will happen if we change the what we call as the current, right? If we change the current, right? Now let's suppose N1 are the turns in this primary circuit, and Phi1 will be the flux linked with this primary circuit. So this N1 Phi1 will be directly proportional to this. N1 Phi1 will be directly proportional to this what we call as the current in the secondary circuit. That's I2, right? So I2 is the current in the secondary circuit. So I2 is the current in the secondary circuit. So I2 is the current in the secondary circuit. So removing this proportionality with a constant, that constant we call as coefficient of mutual inductance. And this coefficient of mutual inductance is nothing. It's N1 Phi1 upon I2, right? Now this M is nothing. It's equal to N1 Phi1 upon I2, right? Now the question is that if we change the current, right? If we change the current with respect to the time, it means that if the current is changed, then the flux linked with the primary coil will also change, right? Flux linked with the primary coil will also change. It means that N1 Phi1 will be equal to M times I2, right? M times I2. If we take the derivative on both sides with respect to time, it will be N1 T phi N1 Phi1, right? N1 Phi1 D Phi1 upon D2, right? That will be equal to M times di2 upon d2, right? So this is the equation upon taking the derivative on both sides. If we multiply on both sides with a negative sign, we'll be left with minus L1 d phi 1 upon dt. That will be equal to minus m times di2 upon dt, right? di2 upon dt. Now this is nothing. This is nothing. This is according to Faraday's law. This is nothing. This is the induced EMF, right? Induced EMF. So the induced EMF is nothing. Once again, it's equal to minus M Ti2 upon dt, right? Minus M Ti2 upon dt. So this will be the induced EMF. This is nothing. This is the induced EMF in a circuit, right? Induced EMF in a circuit, in primary circuit. Induced EMF in primary coil. Now the question is that we have to also find the coefficient of this mutual inductance, right? The coefficient of this mutual inductance we have to also find. So coefficient of mutual inductance is nothing. Coefficient of mutual inductance, we can see that this coefficient of mutual inductance is equal to N1 phi 1 upon I2, right? It's M, that's equal to N1 phi 1 upon I2, right? N1 phi 1 upon I2. Now phi 1 is the flux through the primary, and this flux is because of the magnetic field, external magnetic field. That magnetic field is because of the secondary coil, right? Or we can say that we can write this phi 1 as magnetic field, that's because of the secondary coil, that we can write as B2, right? Right? It's in the primary coil, we can write it as A1, right? B2 A1. This will be the flux linked with the primary coil because of the secondary coil, right? And we know that if this is a solenoid, right? If this is a solenoid, if the inductor here is a solenoid, then we can say that a magnetic field inside a solenoid is nothing. It's mu naught times Ni, right? Mu naught Ni. Where N is nothing, it's the number of turns per unit length. If the length of the solenoid is L, we can write it as mu naught. N is the total number of turns. I times upon L. L is the length of the conductor, right? N is the length of the conductor. So let's suppose N2 are the length, N2 is the length, total number of turns in secondary coil, right? So it will be mu naught N2 I upon L. And the current through the secondary coil is I2, right? Current through the secondary coil is I2. Now we can replace, substitute the value of phi 1. So the phi 1 will become equal to, it will be mu naught N2 I2 upon L, right? Upon L multiplied by A1, right? Multiplied by A1. So this will be the value of phi 1. So if from here, the coefficient of mutual inductance will be N1 upon I2 multiplied by mu naught N2 I2 A1 upon L, right? From here, I2 and I2 will get cancelled. So once again, from here, we can say actually the coefficient of mutual inductance is independent of the current through the circuit, right? So will be left with mu naught times N1 into N2 multiplied by A1 upon L, right? So this is the coefficient of mutual inductance. This is the coefficient of mutual inductance. So you can say that magnitude of the coefficient of mutual inductance depends upon many factors, right? But current is not one of the factors on which the magnitude of the coefficient of mutual inductance depends, right? We can say that coefficient of mutual inductance is actually independent of the number of turns, right? It's actually independent of the number of turns in a circuit. So the dependence of the coefficient of mutual inductance, you can see that it depends upon the number of turns. That is, it depends upon N1 and N2, right? It depends upon the length of the conductors here. So here the length was L2, so I replaced it with L2. So it also depends upon the lengths of the conductors L1 and L2, right? So it will depend upon the length of the secondary coil. It will depend also on the length of the primary coil as well. And you can see there's a factor what we call as factor A. This is nothing. This is the area of cross section, right? Area of cross section. It means that coefficient of mutual inductance also depends upon the area of cross section. It also depends upon the area of cross section. The factor one that on which the coefficient of mutual inductance depend is the number of turns in the primary coil and the number of turns in the secondary coil, on both the factors. And then it depends upon the coefficient of self inductance also, right? It depends upon this coefficient of self inductance also, right? And then it depends upon the area of cross section. It depends upon the length of the inductor as well, because there is a length factor here, right? There's a length factor here. And magnetic permeability of medium, right? Now let's suppose if this inductor is in some medium, right? If this inductor is in some medium, then coefficient of mutual inductance will be in medium given as mu naught mu m, right? N1 N2 A1 upon L2. So mu m will be the permeability in a medium, right? Permeability in a medium, right? So it will depend upon the medium as well, right? And one more important point is it will depend upon the distance between two coils. It means that if the two coils are close to each other, it means that the flux linked will be more, right? If the two coils are far apart from each other, then the flux linked between the two coils will be less. So the change in flux will be different. Similarly, when the two coils are very near to each other, then the flux linked will be more. So the change of flux will also be different. So it means that it also depends upon the distance between the two coils, right? It also depends upon the distance between the two coils as well, right? It will also depend upon the distance between the two coils. It will not only depend upon the orientation, it will also depend upon the distance between two coils. And orientation of coils is also important. How you are keeping the circuit of primary and the secondary circuit, right? Or how you are directing the two circuits or the two coils with respect to each other. So orientation of the two coils with respect to each other is very important, right? So that's how actually depends how actually the amount of flux is actually established or the linked with the two coils, right? It also depends upon the orientation between two coils. So that's very important. First factor, that was the number of turns and the coefficient of self-inductance, area of cross-section, magnetic permeability. It means medium, right? It depends upon the medium. So in different mediums, mutual inductance will be different, right? It depends upon the orientation and distance between the two coils as well, right? So this was the dependence of the uh, coefficient of mutual inductance. And important point to note is that it does not depend upon the current flowing through the circuit, right? Let's try to solve this question here. It's a very simple question, basic question. The question is that a solenoid has 2000 turns wound over a length of 0.3 meter, right? A solenoid has 2000 turns, number of turns are 2000 here, over a length of zero point 0.3 meters. So the length of this solenoid is actually the length of the solenoid is 0.3 meter. The area of cross section is 1.2 into 10 to the power minus 3 meters square around its central section. A coil of there is another coil around its central section of a coil of 300 turns is closely wound, right? A coil of 300 turns is closely wound if an initial current of 2 ampere is reversed in 0.25 seconds, right? Find the EMF induced, right? So if an initial current of 2 ampere is reversed in 0.25 seconds, so find the EMF induced in the coil, right? It means that the change in current here will be actually by 2 amperes, right? In 0.25 seconds. We have to find the induced EMF, right? We know that the induced EMF in case of mutual inductance is given by m di2 upon dt, right? So this is the induced EMF. This is the equation of the induced EMF. So the induced EMF will be equal to minus m di2 upon dt, right? Di2 upon dt. Or we can write it as di upon dt, right? In short, we can write it as minus m di over dt, right? Di over dt. Now it's given that the change in the current is actually equal to 2 amperes, right? It's 2 ampere change in the current, and in a time span of 0.25 seconds, or we can write it as 1 upon 4 seconds, right? 1 upon 4 seconds. To calculate the EMF, we have to calculate the value of this mutual inductance, right? Value of this mutual inductance or coefficient of this mutual inductance. We know that coefficient of mutual inductance depends upon uh, is given by this equation, that's mu naught n1 n2 a1 upon l2, right? It's actually mu naught n1 n2 a1 upon l, right? A1 upon l, correct? A1 upon l. So the situation is actually like this. We have a bigger coil, right? Like this, like this. This is the bigger coil. And in this big coil, we have placed a smaller coil of smaller area of cross section like this. Now, because of the change in the current in the bigger coil, the magnetic flux linked with the smaller coil actually changes, and because of that, EMF gets induced in the central coil, right? And this coil is having a number of turns as, let's suppose N1 are the number of turns here, that's 300, and N2 are the number of turns of the bigger coil, that's given as 2000 turns, right? 2000 turns, correct? 2000 turns. 2000 turns are the number of turns in the bigger coil, right? So the coefficient of mutual inductance will be M, that will be equal to mu naught. Mu naught is 4 pi into 10 to the power minus 7, right? And N1 is 300 and N2 is given here as 2000. And the area of cross section will be the area of cross section of this wire, because flux is linked with this wire, right? So with this wire, the flux will be linked. So the area of this smaller wire is given as, the area of cross section is, okay, the area of cross section is given as 1.2 into 10 to the power minus 3, right? So area of cross section is given as 1.2 into 10 to the power minus 3 meters squares, right? And the length of this conductor is given as L, that's equal to 0.3, right? That's equal to 0.3. So L has value 0.3. We can substitute the value of A here. We'll be left with A upon L, right? So finally, the coefficient of mutual inductance will be 4 pi 10 to the power minus 7, right? 3 into 2 will be 6. It will be 6 into 10 to the power 5, right? Area is given as 1.2 into 10 to the power minus 3, right? Meters square, right? Upon the length is given as 0.3, 0.3. So it will be actually 0.34, right? Okay. So we'll be left with, it will be actually equal to 16. 16, 4 into 4 will be 16, and 16 into 6 will be, 16 into 6 will be 96, right? It will be 96 pi here. And 10 to the power minus 7 minus 10 and plus 5, it will be 10 to the power minus 5, right? 10 to the power minus 5. So this will be the coefficient of mutual inductance. This will be the value of coefficient of mutual inductance, or we can write it as 96 pi, or we can write it as 9.6 pi, 9.6 pi into 10 to the power minus 4. So this is the value of the coefficient of mutual inductance. So if this is the value of coefficient of mutual inductance, we know the value of Di here, right? So Di, we can substitute the value of coefficient of mutual inductance here in this equation. It will be 9.6 pi into 10 to the power minus 4 multiplied by the change in the current, that's 2 ampere, upon the time, that's 0.25 seconds. So this will be the induced EMF, right? This is nothing, this is the induced EMF. So this much of EMF will be induced in the next coil, right? So this is the concept of the mutual inductance. This is how we can calculate the induced EMF or the mutual inductance between the two coils, right? Now the question is, how actually when EMF is induced because of the change in the magnetic flux, or because of the change in the magnetic field, or the change in the current in a circuit, then EMF is induced. Because of that EMF induced, uh, energy gets stored in an inductor, right? Energy gets stored in an inductor, right? So we have to calculate that energy, right? We have to calculate that energy. How much energy actually gets stored, right? So we know that induced EMF is nothing. Induced EMF is actually minus L di by dt. So this much of EMF is getting induced inside of an inductor, right? Minus L di by dt will be the amount of induced EMF. It will depend upon the rate of change of current, right? Inside the circuit or inside the inductor. If this is the inductor, if the current is changing or varying in the flux change, the EMF will be induced. So it will depend upon how actually the current changes, right? And this, if we have to calculate the power, right? Power supplied to this inductor. So the power P will be actually, that will be equal to induced EMF multiplied by the current. So the induced EMF is minus L I Ti by dt. This will be the power, right? This will be the rate at which the work is done, or we can write it as dw over dt. So this is the rate of doing the work. So this is the rate of doing the work in this inductor, right? For this inductor. So dw over dt will be minus Li di over dt, right? And this work done will be actually stored in the form of a potential energy, or we can say this work done will be stored in the form of a magnetic field, right? This energy will be stored in the form of a magnetic field in this inductor, right? In this inductor, the energy will be stored in the form of a magnetic field, right? In the form of a magnetic field, the energy will be stored in this inductor, right? So in the form of a magnetic field, energy will be stored in this inductor, or we can write this dw as dw will be nothing. It will be equal to dw will be actually equal to minus Li ti, right? This will be the dw, right? Because this dt and dt will get cancelled, we will be left with dw only. And from here, if we have to calculate the amount of energy, right? So this amount of potential energy will be actually dw will be equal to minus du, right? This will be the amount of potential energy that will be equal to minus Li ti, right? Minus Li ti. So from here, du will be equal to Li di, right? Now we have to integrate it on both sides to calculate the total energy stored in this inductor, right? So it will be equal to u, that will be equal to L is a constant. It will be integrating it from 0 to I, right? So it will be L I square upon 2, right? Li square upon 2. So this is half Li square. Now the question is that this, what is this I? Now I is the final current, right? The current was initially varying. Now the current was initially varying. This is the point. This I is the value of that current where di over dt is 0, right? Di over dt is 0. At this point, the current does not further change, right? It's fully the energy the energy stored in this inductor is Li square upon 2, where di by dt at this point will be actually equal to 0. Now there will be no further change in the current or no further variation in the current, right? So this will be the maximum amount of energy stored in this inductor, or we can say energy stored inside an inductor is nothing. It's half Li square. Half Li square will be the amount of energy stored in an inductor, right? So amount of energy stored in an inductor is nothing. It's half Li square. Half Li square is the amount of energy stored in an inductor, and this energy is stored in the form of a magnetic field inside a conductor or inductor, right? Once this inductor is once this inductor contains an energy of half Li square, right? Now there cannot be a further change in the current, right? There cannot be a further change in current at this moment. Let's suppose we have an inductor, right? Inductor. Now it was initially fully the current was supplied to this inductor, right? And the energy stored in this inductor was actually uh, half Li square. Now what we can do is that if we just connect this inductor with an external resistor, right? Connect this inductor with an external resistor, then what is going to happen? Now this inductor will become the source of energy for this circuit, and the current will flow through this circuit, right? And the current will start flowing through this circuit. Now, the case is that now it will be because the current in this circuit will be now because of the inductor, because of the energy stored in this inductor, right? So energy will be dissipated, or we can say source of source of current is an inductor here, right? Is an inductor here in this circuit, and energy will be dissipated continuously till the total energy becomes zero for this circuit, right? Source of current is an inductor for this circuit, right? For this circuit, source of energy is an inductor, right? So this will be the amount of energy stored in this inductor, right? Now we have to find out the magnetic energy per unit volume, right? Also magnetic energy per unit volume or energy density, right? Energy density stored in an inductor, right? Energy density in an inductor. Let's suppose we know that energy stored in an inductor is nothing. That's equal to half Li square, right? Half Li square. And let's suppose this is our inductor, right? This is the inductor, and the energy stored in this inductor is half Li square. Energy stored in this inductor is half Li square. We know that the value of L, that's the coefficient of self-inductance that we calculated for this was actually given by this value, that's mu naught n square A by L, right? Mu naught n square A by L. This was the coefficient of the self-inductance, right? Coefficient of self-inductance was given as mu naught n square A by L in case of solenoid. If the inductor is a solenoid, right? Solenoidal in nature. So L was equal to mu naught n square A upon L, right? Mu naught n square A upon L was the value of this coefficient of mutual self-inductance, right? Coefficient of the self-inductance, where L is the length of this conductor, right? We can write it with small l, right? Let's suppose length of this conductor is small l. So this is what we call as the coefficient of self-inductance for this circuit, right? Now let's suppose if we multiply above with length of this conductor and below also with the length of this conductor, so it will be L square in the denominator, or we can say the coefficient of self-inductance will be equal to mu naught n upon L, that's number of turns per unit length, and multiplied by the A into L. A into L is nothing, area of cross section for this, right? Let's suppose A is the cross section for this inductor or the conductor, and area of cross section of the conductor multiplied with the length of the conductor will nothing, it will give us the volume of the conductor. So volume is nothing, it's A multiplied by L, that's nothing, it's the volume of inductor, right? Or volume of solenoid here. So this is nothing, it's the volume of solenoid here. So we can write it here. N upon L is nothing. It's number of turns per unit length. We can write it with the small l. So our L will be mu naught n square, right, multiplied by V, right? Now replacing this value of L, that's the coefficient of self-inductance in this equation. We can write this. This is the energy, half L, that's mu naught n square V multiplied by I square, right? So this half mu naught n square V multiplied by the factor I square. Now, if we take this volume on the LHS, we'll get energy per unit volume, right? We'll get energy per unit volume. That's mu naught n square I square upon 2, right? And this is nothing. This is energy per unit volume. This is nothing. This is energy per unit volume, right? Per unit volume. And this is what we call as energy density, right? Energy per unit volume, we call it as energy density. So energy density is nothing, it's the energy per unit volume, right? So this is the energy per unit volume. Now let's rearrange it. We can write it as ED. It means we're talking about the energy density. That's equal to mu naught n square I square over 2, right? Mu naught n square I square over 2, correct? Now we can do a little bit modification in this. We know that the magnetic field in case of solenoid is nothing, it's mu naught Ni, right? Mu naught Ni, correct? Mu naught Ni, right? So let's replace this N by P upon mu naught I, right? Mu naught I. Now we can replace this N with P upon mu naught I. We'll be left with mu naught times, it will be P upon mu naught I whole square multiplied by this factor I square upon 2, right? Upon 2. So from here what we get, it will be mu naught P square I square upon mu naught square I square into 2, right? So from here I square and I square will get cancelled, mu naught and mu naught will get cancelled, we'll be left with P square upon 2 mu naught, right? So this is the energy density stored in this inductor. So the energy density of an inductor is nothing, it's P square upon 2 mu naught. So B square upon 2 mu naught is the energy stored in this, or the energy density for this inductor. We know in case of solenoid, for a solenoid, P has the constant value, that's mu naught Ni, right? mu naught Ni. So if B is a uniform magnetic field, then the energy density will be given by B square upon 2 mu naught. Or this is the energy density stored in this inductor, right? Or in this solenoid, right? So we get the value of energy density as P square upon twice mu naught. So the P square upon twice mu naught is the energy density for this energy stored in this inductor, right? Now let's move on to the next short topic, right? We'll be very soon concluding this chapter, that will be EMI, and in the next class we'll be starting with the AC alternating currents, right? You can see here when we discussed about the induction induced EMF, we discussed about the methods or the ways we can actually induce an EMF in a conductor, right? There was a way by changing the magnetic field, right? We can also induce the EMF inside the conductor by changing the area of cross section, right? Or area of a loop. And there was important factor, that was the orientation of the area vector with respect to the magnetic field vector, right? When we discussed when we discussed the flux phi, that was equal to PA cos theta for a uniform field, right? For a uniform magnetic field. So flux through any area of cross section A is given by BA cos theta, or we can say it's actually B dot A, or we can also see that it depends upon the angle theta, which is the angle between the area vector and the magnetic field vector. So from this, it means that the flux linked with the coil depends upon the orientation of the magnetic field with respect to the area vector, right? Now, by changing the orientation of field vector and the area vector with respect to each other, then the flux linked with the coil will change, and it will eventually result in the induction of an EMF, right? Induction of an EMF. So for this situation, we'll be studying about the periodic EMI, right? Uh, a periodic, right? A periodic EMF is induced by changing the orientation of magnetic field with respect to the area vector, right? You can see here, we have a coil initially placed perpendicular to uniform magnetic field. Now this coil starts a rotation about an axis, right? This is the axis. You can see this is the axis about which this coil actually starts a rotation, right? What is the cause of rotation? The cause of rotation can be anything, right? Now let's suppose, now because of something, this coil is actually rotating, right? Because of some external agent which is rotating it, right? The coil change, flux linked with the coil will change due to the change in orientation, because we know that when orientation change with respect to area vector and magnetic field vector, then the definitely flux will be different and the flux is going to change. If the flux change, the EMF will be induced, right? Now let's suppose at any time t, the orientation, initially it was at 90-degree angle. If at any time t, the orientation of magnetic field vector with respect to area vector is theta, right? Is theta, and initially the angle between them is actually 0 degree, right? If initially the angle between them is 0 degree, it means initial orientation is 0, or we can say at time t equal to 0, if theta is equal to 0 degree, and at time t equal to t, right, there is some orientation theta, that's equal to theta, right? That's equal to theta, right? So flux at any instant will be given by pa cos of theta, right? Pa cos of theta, pa cos of theta. Now if we take the derivative on both sides, that's d phi over dt, right? That will be equal to d over dt of PA cos of theta, right? PA cos of theta, correct? PA cos of theta. So it will be equal to PA times d over dt of cos of theta. And we know that derivative of cos of theta is nothing, it's minus sine of theta, right? It's minus sine of theta. So it will be minus PA sine of theta, right? Sine of theta, correct? So that's our d phi over dt, right? Now let's suppose for n number of coils. You can see here in this coil there are n number of turns. For n number of turns, for n number of for n number of turns, for n number of turns. So flux will be actually n d phi over dt, right? that will be equal to minus NBA sine of theta, right? Minus NBA sine of theta, right? If we multiply, if we multiply on both sides with a negative sign, so it will be minus n d phi over dt, it will be plus NBA sine theta, right? And this term is nothing. This is what we call as the EMF, right? This is nothing. That's the EMF, right? That's the EMF induced. That's the EMF induced. If this is the induced EMF, it means that we get the induced EMF as NBA sine of theta, right? NBA sine of theta, right? And this theta is the nothing amount of rotation from time t equal to 0 to time t equal to t. This is the amount of rotation. And we know that uh, since it's a constant omega, right? If omega is constant, we can replace theta with omega t, right? Theta with omega t. So replacing theta with omega t here, it will be NBA sine of omega t. Sine of omega t, right? So we know that sine of theta is a periodic function, right? It's a periodic function. And similarly here, EMF is a function of sine of omega t, right? Or we can say it's a sinusoidal, EMF has the nature of sine function, right? That's why we say it's a periodic EMI, right? So it means that this EMF will also have a periodicity, right? It will behave like a sine curve, right? It will behave like a sine curve. It will behave like a sine curve. So our EMF is coming out to be equal. EMF will be equal to NBA sine of omega t, right? Sine of omega t. Now this NBA will be nothing. Let's suppose omega t is equal to pi by 2, right? If omega t is equal to pi by 2, then sine of omega t will be equal to sine of omega t will be equal to uh, that will be equal to 1, right? That will be equal to 1. Now the question is that what is this omega? This omega is nothing. This is what we call as angular frequency here, right? It's the angular frequency. It's the angular frequency here. Now, if this omega is the angular frequency and this omega is nothing, it's given by 2 pi times the frequency of this rotation, right? And the value of when sine omega t is equal to 1 or omega t is equal to pi by 2, sine omega t is equal to 1, then E has the value of NBA, right? NBA. So this is nothing. This is the maximum value of induced EMF. This is nothing. This is the maximum value of induced EMF. Maximum value of induced EMF. So this is nothing. This is the maximum value of induced EMF. If this is the maximum value of induced EMF, we can plot this induced EMF, right? Induced EMF with respect to time, right? EMF versus time, right? It will be nothing. It will behave like a sine curve, right? So this is how the EMF will be like with a constant time period, right? The constant time period. And the maximum value of this induced EMF will be that's equal to NBA, right? That's NBA. And the minimum value will be this. This will be nothing. It will be minus NBA. It will be minus NBA, right? And you can see after here, actually the current is EMF is increasing and becoming the maximum, and then it continuously increases and becomes maximum at this point, and then continuously decreases, becomes zero, right? Becomes zero. It means that in a one complete cycle, right? The EMF becomes actually zero. At time t equal to zero, EMF is zero, right? At time t equal to uh, let's suppose this is omega t. If we call this as omega t, then this will be equal to pi, right? This will be pi, this will be 0, right? And this will be 3 pi by 2 over here. And this period will be here 2 pi, right? So the complete period for this function will be omega t is equal to 2 pi will be the period for this curve, right? So here the maximum EMF is maximum here, right? EMF is 0 here, and the EMF is uh, minimum here, right? Is the minus NBA value, right? So you can see that here The EMF is continuously changing, and it is first increasing, then becoming maximum, then decreasing, right? And becomes maximum in the negative direction, then once again comes back and becomes zero, and then once again repeats the cycle, so on and so forth, right? So you can see the direction of the EMF is changing, right? Direction of the EMF is changing. So because of this, we can say we say that we call this EMF as alternating, right? This is alternating because of the change in the direction of the cycle, right? Change in the direction of the induced EMF. So this is the alternating, and the current because of this alternating EMF is what we call as alternating current. The current because of it is nothing. That's given by E upon R, right? That's nothing. That's equal to NB A over R multiplied with the factor sine of omega t. Multiplied by the factor sine of omega t. So this will be the induced current, right? This is what we call as this is the induced current, right? And this from here it gives rise to the alternating current, right? We'll be discussing in the next chapter the alternating current, how actually the alternating current behaves for different electrical elements, right? For capacitors, for inductors, for resistors, right? That will be discussed in the next chapter in detail, right? So this is how actually the induced EMF varies, right, with respect to the rotation of this coil, or we can say if the orientation of the magnetic field vector changes with the area vector, right? Changes with the area vector. So NBA upon R, NBA upon R will be the maximum value of this current, or we can say I is nothing. It's equal to I naught sine of omega t. I naught sine of omega t. Correct. I naught sine of omega t, or this I naught is nothing. We can call it as maximum value of the current. That's I max. That's nothing. That's NBA over R, right? NBA over R. So this is the maximum value of the current for this circuit, right? Now we'll be discussing some of the miscellaneous concepts, right? Very small, minor concepts here. One of the important concept here is the eddy currents, right? So eddy currents are nothing. These are basically the induced current, right? These are the induced currents set up inside a conductor, right? Because of the change in the magnetic flux, right? Whenever magnetic flux changes inside the body of a conductor, then small, very small currents get induced, right? And those currents we call as eddy currents, right? And the property of these currents is that they always tend to follow the path of least resistance, right? They follow the path of least resistance inside a conductor, so that they always form a irregular shaped loops, right? They form a loops, closed loops, right? So that's the property of eddy current. So they are actually developed because of the change in the magnetic flux, right? Right? They are changed by the magnetic flux, and direction of these eddy currents are actually very random, right? They form the a path of least resistance with the random directions, or they form very irregular loops. Like this here in this picture, you can see here some of the eddy currents are developed in this metal disc, right? Because of the change in the flux, right? Eddy currents are developed, and these eddy currents try to form the closed loops, right? They form the closed loops, right? Irregularly shaped, sometimes regular, sometimes irregular, right? And the direction of these eddy currents inside a metal body or metal sheets are very random, right? So these are the currents, and they usually follow the Lenz law as well, right? Because Lenz law, you know that it's a consequence of the law of conservation of energy, right? Law of conservation of energy. So they have to follow the Lenz law as well, right? But one of the important points about the eddy currents is that their applications, right? Their applications. Eddy currents are having a tremendous applications in our daily life, right? We use induction furnaces, right? That's actually the application of the eddy currents. We electromagnetic damping. It's one of the important application of the eddy currents. And in our vehicles or transport system, we use electric brakes, right? And those electric brakes are actually run by these eddy currents, right? So because of the eddy currents, we actually are able to get the electric brakes or the high efficiency brakes in our transport systems, right? Similarly, speedometers, induction motor, these are all applications of the eddy currents, right? So these are some of the very common applications that we use, right, in our daily lives. So one of the important applications is the electric brakes. So in electric brakes or in trains also, we use the concept of the eddy currents to use the electromagnetic brakes, right? So that's the concept of the electric brakes in case of transport system. It's all because of the eddy currents, right? Now let's try to solve some of the uh, questions asked in your previous exams, right? So it's a very basic question on your screen. You can see that a magnetic field of 0.3 Tesla is directly perpendicular to a rectangular loop. If the loop's dimensions are 0.1 meter by 0.2 meter and the magnetic field changes at a rate of 0.5 Tesla, right, per second, what is the induced EMF in the loop? So it means that we have this loop, right? This is the loop. This is nothing. This is the loop, right? And in this loop, it's having a dimensions of 0.1 meter and 0.2 meter are its dimensions, right? And the magnetic field changes at a rate of zero point 0.5 Tesla. And we know that EMF is nothing, it's d phi over dt, right? D phi over dt, correct? So d phi over dt, we can write it as d over dt of uh, PA, right? PA, right? That's our flux. That's our flux. So induced EMF will be nothing. Area of this loop is a constant. We'll take it outside. It will be A dB over dt, right? dB over dt. Now a magnetic field of 0.3 Tesla, right? Uh, is directly perpendicular to a rectangular loop if the loop's dimension and the magnetic field change at a rate of zero point 0.5 Tesla per second. Now the rate of change of this magnetic field is 0.5 Tesla, right? So dB or dt is 0.5. We'll write here 0.5 multiplied by the area. That's 0.2 multiplied by 0.1, right? So it will be nothing. It will be actually equal to 10 multiplied by 10 multiplied by it will be 10 to the power minus 3, right? Or we can write it as 10 to the power minus 2, right? So this is the induced EMF, right? This is the induced EMF in this loop, right? This will be the amount of induced EMF. Now, next question is a coil with a resistance of 10 ohms and inductance of 0.02 Henry is connected to a circuit with a switch. If the current changes from 0 to 5 ampere in 2 seconds, when the switch is closed, what is the induced EMF, right? Now, once again, this is the conductor, right? This is the conductor, and there is some circuit, right? There is some circuit, right? And the circuit is having a resistance of 10 ohm, right? And this inductor is having a coefficient of self-inductance as 0.02 Henry, right? Right. If the current changes from 0 to 5 amperes, or we can say delta I is nothing, that's equal to 5 amperes, right? In time, delta t, that's equal to 2 seconds, right? 2 seconds. Now the induced EMF will be equal to LDI over dt, right? LDI over dt, right? So this induced EMF will be L, the value of L is 0.02 multiplied by the amount of change in current, that's 5 ampere, because current changed from 0 ampere to 5 ampere. We can write di as 5 upon delta t or dt, that's 2 seconds, right? It will be upon 2, right? So it will be actually equal to 0.05, right? 0.05 volt. That will be established in this circuit. So the induced EMF will be 0.05 volt, right? So this much will be the induced EMF in this circuit. So that's it. These were some of the questions, past year questions, right? So in the next lecture, we'll be dealing with the new chapter, that is the alternating current, right? So we'll be discussing the alternating current in the next lecture. Till then, take care and goodbye.